All right, welcome back, and here we go with trig equations part 2. First off, we're going to talk about how we can sometimes use trig identities to solve the problems. And our first example is going to be example number 7, which is 2 cosine squared x plus 3 sine x equals 0. So we have a cosine and a sine together, and that really doesn't get us very far. So what we want to do is we're going to change, oh, and by the way, we want to keep it between 0 and 2 pi. So I'm going to change my cosine squared x to 1 minus sine squared x. I'm going to use that Pythagorean identity to do that. So now when I distribute the 2, I have 2 minus 2 sine squared x plus 3 sine x equals 0. Or minus 2 sine squared x plus 3 sine x plus 2 equals 0 when I change the order just so that it's in quadratic equation form. Now I don't like having a lead negative sign, and since the right hand sign is 0, I can go ahead and multiply through by minus 1, and that just changes all my signs. So here's what we're working with: 2 sine squared x minus 3 sine x minus 2 equals 0. And we have a sine squared and a sine. And how do we factor that? Well, it's going to be 2 sine x and sine x will be my first terms because I don't have any other choice. And my last term I know is going to be a 2 and a 1. And I notice that if I put them here and make the 1 a plus and a 2 a minus, then I have my 2 sine squared x minus 3 sine x minus 2 equals 0. So this means that sine of x equals negative 1/2, or sine of x equals 2. Now you can see right away we have a little bit of a boo-boo here because you can't have sine of x equals 2. The greatest value for sine of x is 1 and the least is negative 1. So we just scratch that guy out. So this means the sine of x is negative in the third and fourth quadrant. So I'm going to have 7 pi over 6 in the third quadrant, and I'm going to have 11 pi over 6 in the fourth quadrant. So those are my two answers. Okay, so go ahead and I have checkpoint 9. I hope that's the right one. I think it might be 7, so you check it out. Okay, so example 8. Yeah, that should have been checkpoint 7. Sorry about that. Let's use identities again. So I have cosine 2x plus 3 sine x minus 2 equals 0. And once again, I have cosines and sines together. And I am going to keep this again in the 0 to 2 pi interval. Cosine 2x is equal to 1 minus sine squared x. Now why did I change that? Because I have to have them match up. And this is easier to change the cosine 2x to something with sine and then keep going with my plus 3 sine x minus 2 equals 0. So when I clean this up, I'll have minus 2 sine squared x plus 3 sine x minus 1 equals 0. And multiplying through by negative 1 because I don't like that leading negative 2. 2 sine squared x minus 3 sine x plus 1 equals 0. And that factors to 2 sine x and sine x for the first terms. And of course 1 and 1 because you have no other choice. So if I put both negatives in here, then I have my middle term of minus 3 sine x and my last term of plus 1. So that means that the sine of x equals 1/2, or the sine of x equals 1. Sine of x equals 1/2 in quadrant 1 and quadrant 2. So it's going to be pi over 6 and pi minus pi over 6, which is 5 pi over 6. And the sine of x, whoops, there we go, circle those bad boys. And the sine of x equals 1 at pi over 2. So my answer is x is pi over 6, pi over 2, and 5 pi over 6. So go ahead and do your checkpoint 8. I'm back on track with my numbering system here. All right, example 9. Using both sides of the equation. So if I have sine x cosine x equals 1/2, and I want to restrict it once again to 0, between 0 and 2 pi. Be careful because I'm just liable to slip another interval in there. I might go from 0 to 4 pi, which means you're going to have more answers. So just heads up on that one. You know how sneaky I can be. So I am going to multiply both sides by 2, which gives me 2 sine x cosine x equals 1, and which is going to give me sine of 2x equals 1 because 2 sine x cosine x is equal to sine 2x. Remember those double angle formulas. All right, so sine of 2x equals 1. Now, where is the sine of theta, or sine of anything, equal to 1? Well, that's when theta is pi over 2. So 2x equals pi over 2 plus 2n pi. Remember, we have to keep that 2n pi in there because we have a multiple angle formula here, and we're liable to have some more answers. So now when I solve for x, I get x equals pi over 4 plus 2n pi over 2. I'm sorry, divide by 2, not multiply by 2. Anyway, x equals pi plus 4n pi over 4 when we put them together. Okay, so we got that. Now, when n equals 0, the answer is going to be, x is going to be pi over 4. When n equals 1, it's going to be 5 pi over 4. That's not 2 pi yet, so we can keep going. When n equals 2, it's 9 pi over 4, but that's bigger than 2 pi. So there are my answers for that one. Pi over 4 and 5 pi over 4. Okay, so go ahead and do your checkpoint number 9. Okay, number 10. Sine x minus cosine x equals 1. Wow, where do we start with this one? Well, you know, when all else fails, remember that as long as you do the same thing to both sides of the equation, you're okay. And I know that if I have just a sine x and a cosine x, that's getting me nowhere. But if I can make a sine squared and a cosine squared, then I'm going to be able to get somewhere. So I am going to square both sides. Now you got to be careful when you square both sides of an equation. When you get your final answers, you have to check them out to make sure that you don't have any extraneous answers. All right? Okay, be careful. Possible extraneous roots. Okay, so we have, when we square this binomial, we have the trinomial sine squared x minus 2 sine x cosine x plus cosine squared x equals 1. All right? Now what I'm going to do is I'm going to put my sine x and cosine squared x and cosine squared x together. And you know what that gives me? Well, that gives me a 1. So I'll have 1 minus 2 sine x cosine x equals 1. If I subtract 1 from both sides, then I have minus 2 sine x cosine x equals 0. So now I have something I can factor. Okay, so that means either sine x equals 0 or cosine x equals 0. Well, sine x equals 0 at 0 and pi, and cosine x equals 0 at pi over 2 and 3 pi over 2. Now, if you just put those 4 answers down, you've got your 4 possible answers, but you've got to go back and plug them into your original equation to make sure that they work. So sine of 0, remember the original equation is sine x minus cosine x equals 1. So sine of 0 minus cosine of 0 equals 1 gives us a negative 1 equals 1, which does not work. So 0 is not an answer. All right, let's try the next one. Sine of pi minus cosine of pi equals 1. Well, that's going to be 0 minus a minus 1, which is 1 equals 1. So that works. So pi is an answer. The next one, sine of pi over 2 cosine pi over 2 equals 1. Sine of pi over 2 is 1. Cosine pi over 2 is 0. And 1 minus 0 equals 1. So we're okay there. 3 pi over 2 is going to give us a sine of 3 pi over 2 is negative 1 minus cosine 3 pi over 2 is 0. That would give us minus 1 equals 1, which is not true. So that is extraneous also. So our answers are x equal pi and pi over 2. All right, go ahead and do your checkpoint number 10 and watch out for extraneous answers. Be on the lookout. Example 11. Solve with a calculator. Okay, this is going to take a little practice, and we're going to be dealing with numbers that are rounded to 4 decimal places, but you're going to work this the same way as you would just thinking of about a pi over 6 or a pi over 3 or a pi over 4. Okay, so we want to solve this to 4 decimal places. Hang in there. If I have the problem tangent x equals 12.8044, and remember tangent can go to negative infinity and positive infinity, so this is not an impossible problem. So I'm going to think of this as that's my original problem. Now I'm going to change it. I'm going to think about tangent of theta in general as 12.8044. And I want to solve for theta in quadrant 1. We're just going to worry about quadrant 1 to begin with. So theta is now going to be, if we want to solve for theta, this is when we use the inverse tangent or arctan. So it's tangent to the -1. Remember, in your calculator, it's going to be second tangent, and then you put 12.8044 in there. And there you go. I remember to write that down. And so theta is approximately, the little dot over the equal sign is the same thing as the two little squiggly equal signs. Okay, so it's 1.4929. Okay, now, but we know that tangent is positive in more than one place. So we go back here and we know tangent is greater than 0 in quadrant 1 and quadrant 3. So we know that we're going to have x is going to be approximately 1.4929. That's in quadrant 1. In quadrant 3, I'm going to take that value and add pi to it. And you can just use, on your calculator, just do 1.4929 plus, and then put your actual pi in there. Okay, second, whatever pi is over on the, I forget, on the calculator, which is going to give you 4.6345. Okay? So there's my two possibilities there. Let's try another one. Let's try cosine x equals negative 0.4317. All right, so we're going to change this to cosine theta is positive 0.4317, because we're really just trying to find that reference angle for right now. So that means that theta is going to be the inverse cosine of 0.4317, which gives us 1.1244. Okay? Remember, that's in the first quadrant. But now we want to find out, where is the cosine negative? Cosine is negative in the second and third quadrants. So what we're going to do is we're going to take our pi minus our 1.1244, and that's going to give us the second quadrant, which is 2.0172. And then we also went pi plus 1.244, because that would put us into the third quadrant, which is 4.2660. So there's our two answers for that. Think about it the same way as you're using your pi plus pi over 6 or pi plus pi over 4 or whatever. It's just now you're working with decimals. And please remember to always say that it's an approximation, because we're rounding it to 4 decimal places. Okay, so do your next checkpoint number 11. Okay, example number 12. We're going to use a quadratic formula with a calculator. Everybody loves their calculator. So solve correct to 4 decimal places. Sine squared x minus sine x minus 1 equals 0. Okay, in here, and I want to caution you, and once again, we tend to use x for everything, and sometimes it gets us into a little bit of trouble. So I hope that I hope that I can explain this clearly enough. In here, a is 1, b is -1, c is -1, and we are using, and I'm going to go back to using that u, and u is going to represent sine of x. So u is negative b plus or minus square root of b squared minus 4ac over 2a. We all remember that. Okay? And u is going to represent sine of x. So when I plug my numbers in, and I'm going to leave this up to you, I'm not going to read this whole thing off to you because I'll probably trip all over it. Anyway, when I solve it, I come up with u is 1 plus or minus the square root of 5 over 2. When I use the positive root, or the positive square root of 5, I get 1.6180. And that can't be, because the sine of x cannot be bigger than 1. So that's one of those things that just don't work. Okay, and 1 minus the square root of 5 over 2 is going to be negative 0.6180, which does work. Okay, so we have sine of x equals negative 0.6180. All right, so we want to solve where is the sine of x, sine of theta, 0.6180. Well, it's going to be, theta is going to be, when we use the inverse sine or arc sine, 0.6662. But now we want to know, where is it less than 0, where is it negative? And sine is negative in 3 and 4. So our reference angle of 0.6662, defined in quadrant 3, we would say pi plus 0.6662 is 3.8078 approximately. And in quadrant 4, we would do 2 pi minus 0.6662. And once again, you use your pi key on your calculator, and that gives you approximately 5.6170. Phew, that's a lot of numbers. All right? Okay, so go ahead and do your checkpoint number 12. And guess what, folks? We're all done. This is a big old mouthful for everybody, and I hope you go back through this a couple of times, and I will see you in class. Bye.